Everyone, welcome to week 5 of the live problem solving session for the course on traffic engineering offered through NPTEL. My name is Sethi Vinayagam. I am a PhD scholar in the civil engineering department at IIT Madras. So let's start with an overview of the concepts that were taught in week 5 of the lectures. Okay, so this week we had 6 lectures in total. So first lecture, so we continued with the analysis of two-lane highway segments. Right. So last week we left with the LOS and the capacity analysis for the two-way highway segments as per the HCM. Okay. So this week we continued with it. So what we looked at, we saw, what is the framework that is used for LOS determination when it comes to two-lane highways. Right. So before this we were looking at multi-lane highways. Right. But here we are looking at two-lane highways. So what is different from multi-lane highways and freeways is that we two-lane highways. So these are slightly lesser capacity facilities, right? They are not as in terms of functional classification, they are not going to offer as high mobility as the multi-lane or the freeways. So therefore we have to analyze them separately. So when it comes to the framework, so we have three different types or classes of two-lane highways. Right. So we have looked at this earlier. So we have class 1, class 2, and then class 3. Right. So these three have to be separately analyzed. Right. So we have to determine what is the type of two-lane highway that we are analyzing, and then accordingly the framework changes or the steps that are involved for the LOS analysis differs. So for class 1 and class 2, so these are facilities that exist in the rural region, whereas class 3 is present in the urban region. Okay. So for class 1, so what do we do? So first step is to estimate the free flow speed. Okay, so that is the first step. So once we know the free flow speed, so then we have to see the performance measure also differs. So the performance measure for class 1 is the average travel speed and the percentage time spent following, right? So these two. So first, for the first performance measure, which is ATS, so we have to find the adjusted demand, right? So demand adjustment for ATS, right? So we measure some demand, but it has to be adjusted, for the ATS based on the current field conditions. So which accounts for the gradient, right? So the terrain condition and also the presence of heavy vehicles and recreational vehicles, right? So these two adjustment factors have to be used for adjusting the demand for ATS calculation. So once we have the adjusted demand, we go for ATS estimation, right? So that gives us ATS. Second, we have to do for the PTSF, right? So same demand adjustment, but now for PTS. For PTSF, right? So once we have that, so we go for estimating the PTSF. So then we use the ATS and the PTSF, right? So the two performance measures to determine what is the LOS for the class 1 units, right? So class 2. So here the difference is that there is no two measures, right? So there is only one performance measure for class 2 highways, which is only the PTSF, right? So ATS is not used for class 2 two-lane highways. So therefore, this step demand adjustment for ATS will not happen. So directly we go for the demand adjustment for PTSF, estimate the PTSF, and then go for the LOS determination. So when it comes to class 3, so class 3, as I said, this is in urban area. So here the performance is different from class 1 and class 2. So the measure is percentage of the free flow speed, right? So here we, instead of using ATS or PTSF, we go for the percentage of the time, percentage of the free flow speed that exists in the highway, right? So speed is the criteria for the LOS in class 3. So here, yes, still we need to estimate the free flow speed, because finally we are looking at a percentage of FFS, right? So we need to first get an estimate of the free flow speed. So once we get the free flow speed estimate, then we have to go for the ATS determination. So we have to do demand adjustment for ATS. So why are we calculating ATS? Because this percentage free flow speed, right? The calculation of that, involves ATS, right? So it is basically ATS by FFS. That gives you a PFFS, right? So to get the percentage of free flow speed, we need an estimate of the average travel speed, right? So therefore, we need to find the ATS. So we do the demand adjustment, then get the ATS, then calculate PFFS, and then go for the LOS determination, right? So those are the steps involved, right? So this is the overall framework or the methodology that we use. So that was seen. Then we looked at the detailed computational steps, right? So what are the the adjustment factors involved in each of these steps, which tables from the HCM that we use. So all those were explained. We looked at detailed computational steps, and then finally we looked at some numerical examples as well, for analyzing these two-lane highways. So then in the second lecture, we moved on to looking at urban street segments, right? So till now we were looking at highways, multi-lane freeways, and two-lane highways. Now we are moving into urban street segments, right? So these urban street segments, so these occur. What are these urban segments? They occur in the developed areas, right? So mostly highways, connect different parts, long distance connections, whereas these urban street segments exist within developed areas, right? So basically you will have different intersections, right? So when you look at like a city, so you will be having multiple intersections, and then the roadways connecting these intersections. So those are our urban street segments, right? So we look at between two intersections, right? So the intersections will form the boundary of the segment that we analyze. So as I was saying, so the urban street segments, so they are stretches of road, bounded by the intersections, right? So the two intersections will form the boundary, and then the road segment between these two intersections is what we analyze in the urban street segments. Okay. So in this, so we looked at what are the different types of controls and systems of operations, right? As we have intersections, so they are good there. So conflicts, exist to resolve this, conflicts. So we have some control systems that are, provided, right? So for safe movement of the traffic. So what are the different types of controls that we can have in the intersection? So if there is no control, we call it as an uncontrolled intersection, right? So we just have to use the basic rules of the road, when we are passing through those intersections. But when the volumes are high, we cannot have uncontrolled intersection. We have to go for some kind of control. So we can have signalized intersections, right? So we can install signals, or we can have stop control. So which means you'll have stop signs, which means vehicles have to come, they have to stop, they must stop and then look for a gap and then pass through the intersection, right? So we can have two-way stop control, or we can have all-way stop control intersections, or you can go for passive control, like using roundabouts, right? So these are like different kinds of controls that we can employ in the intersections. And then we have different systems of operation, right? How do these different intersections work, right? So whether whether they are independent of each other, or whether the operation of one and its upstream or the downstream intersection are linked or not, right? So we have within that systems of operation. So we have coordinated and uncoordinated, right? So this is mostly applicable for signalized intersection, right? So what happens in a coordinated signal? Suppose these two intersections are signalized, okay? So suppose when this signal turns green, the vehicles pass through, and then so if the two signals are coordinated, so by the time these vehicles reach the downstream signal, this downstream signal will also turn green, and therefore these vehicles can directly pass through without having to wait, right? So the signal timings are set in such a way that the vehicles will get a through movement without having to stop at multiple intersections, right? So they can pass through multiple signals at a stretch without having to wait at each other, right? So that's the coordinated operation. Uncoordinated means there is no coordination, which means these signals are set independently of each other, right? So it may happen that you have to wait at each signal, right? So that may happen. So depending on this or type of analysis will differ. And for analysis, we have three different types of analysis that we looked at. So one is planning. Depends on the purpose for which we are doing the analysis, right? So one is for planning purpose, another is for design purpose, and third is for operational purpose, right? So if you look at order, so this is from the order. This is the order in terms of that level of detail that is involved, right? So planning is what you do first, right? This is basically to come up with a feasibility report, right? So to look at multiple different solutions, right, and then see which work, which will work and which will not work, and which is feasible, right? So that is the planning study. This is a high level analysis, right? So you don't go into too much details here. So you analyze intersections, assume default values if it is not available, right? So with minimal amount of data collection, so you go for this type of analysis. Then comes the design part. So design part, so you have done the planning, so you have come up with some feasibility report, and then decided to implement some solution, right? Some kind of control system, right? So in that case, you have to design, like the signal, you have to design what are the phases and what are the signal timings, right? So cycle lengths, etc. So that's where the design analysis comes, right? So this involves little more detail, like you need to know little more about the street segment that you are analyzing to come up with a proper design. And then finally, operational part is the day-to-day use, right? So here you need the utmost level of detail. So you need to know exactly the current the field conditions, so that you can operate it in an efficient manner, right? So that is these are the three levels of analysis, and the complexity obviously varies. Like simplest is the planning one, and the most complex one is the operational analysis. So third lecture, so again we continued with the urban street segments. So the previous one was more about theory. So here we looked at how to do the operational analysis, right? So we looked at the different computational steps, right? So the methodology that is behind this operational analysis. And in the fourth lecture, we looked at how to do the planning level analysis, right? And the steps involved and some numerical examples for doing this planning level analysis. So next, in lecture 25, so we were looking at how to analyze single, intermediate, and two-lane roads, right? So even though we have looked at how to analyze this two-lane roads, multi-lane highways, so here we were looking at how to do this using the Indo-HCM, right? So far, the HCM that we have been using for all these LOS and capacity analysis. So these are based on the developed in the US. right? So the HCM, the green book. Whereas the traffic conditions, in India is very dissimilar to what we will see in the US, right? So we have a heterogeneous system of traffic, right? Which means that we have different classes of vehicles, right? So our vehicle composition is very different from what we see there, and also the lane discipline, that is also different. So we need a manual that is more suited for our conditions, right? So therefore, this Indo HCM or the Indian HCM was developed. Okay, so how to use this manual for doing this, same LOS analysis? That's what we were looking at in the last two lectures. So here we were looking at the manual and how to do the analysis. And looked at that, we came across the stream equivalency factor. So what is the stream equivalency factor? So basically, because different vehicles, the characteristics are different. Generally, we use the passenger car unit, right? PCUs as one standardizing factor, right? So instead of counting the number of vehicles, right? So we will count them in terms of PCUs in all our analysis, right? So but this PCU, it depends on the composition, right? So it can change depending on the traffic conditions, the volume, etc. So therefore the stream equivalency factor was introduced, so which takes into account the the flow in the PCU, as well as the flow taken in vehicles per hour, and then comes up with the stream equivalency factor, right? So this was introduced in this HCM, into HCM. That is what we will be using in the analysis. And then we looked at some applications of how to use this manual for analysis. And then in the last lecture, we were looking at the same Indo HCM for multi-lane highway analysis, right? Again, what are the steps involved, and also some examples to carry out that. Okay. So now let's look at some questions related to these concepts in this particular week. Okay. So the first question is, for two-lane highways, which of the following is the preferred method of determining the FFS or the free flow speed? So the options are: A, direct field measurement at flow rates under 200 vehicles per hour in both directions. Option B is adjusted field measurement taken at higher flow rates. And option C is estimating the free flow speed indirectly from the base free flow speed or the BFFS. Okay, so maybe I'll give 1 or 2 minutes to answer, and then we can look at the solution. Okay, so let's take a look at the answer now. The right answer is option A. It is a direct field measurement at flow rates under 200 vehicles per hour in both directions. Okay, so all these three are are ways of estimating the free flow speed, right? So if we go for option A, B, or C, so we will get one value for the free flow speed of that particular facility that we are analyzing, right? So but here the question is which is more preferred, right? So if we can do all the three, right, we will not be doing all the three. We have to pick one. So in that case, which is the one that we would choose, right? So which means we need to understand why what is first free flow speed, right? So we know that speed varies with density, right? Speed and density, as well as it varies with the flow as well, right? So if we look at it, so the speed flow relation for freeways and highways, so it will be looking something like this, right? So we have the speed and we have the flow, right? So which means that until some point the speed remains constant, right? So it is some value of speed. So at low flow conditions it will be remaining constant, and after some point will start decreasing in a non-linear fashion, right? So this particular point is what we call as the break point, right? And this constant speed is our free flow speed. Okay, so it means that at low flow conditions, so the vehicles can travel at a higher speed, which is not under the influence of the surrounding traffic, right? So because at low flows your densities will also be lower, right? Right, so in that condition, the vehicles are too far away from each other, right? So they are not close to each other. So therefore, the vehicles are not impeded by the surrounding traffic, and then therefore they can travel at higher speed, right? So this speed is the free flow speed. So which means that we should be taking these measurements at low flow conditions, right? So which low flow and low density as well, right? So which means where when we are expecting the free flow to occur, right? So the measurement should be taken at that point in time, so that we get the the best or the most closest or the accurate estimate for the free flow speed. So that's the first option, right? So directly estimating from the field. So when the flow is very close to zero, like 200 vehicles per hour, right? With respect to the capacity, so 200 vehicles per hour is a low flow rate. So next is adjusted field measurement taken at higher flow rate, right? So obviously higher flow rate is going to give you a speed that is lower than the free flow speed, right? So the speed that you will see when the flow is high is not going to be the free flow speed. Therefore, you have to make some adjustments, right? So we have some empirical formulas that gives you what will be the free flow speed if you take the measurement at some higher flow rate, right? But obviously this is not going to be as accurate as what we get from A, right? So because A is the actual condition where the free flow exists, right? So the speed that we observe there is at the actual free flow speed. So B is some estimate, so it's going to be somewhat like a like making a guess, right? So based on like our previous relationships that we are using to derive that. And C is estimating FFS indirectly from BFFS, right? So here we are not taking any measurements from the field, right? So the field conditions are ignored, other than for the factors that we take into account when we are deriving the FFS from BFFS, right? So we will have adjustment factors for lane width, the number of the access points, or the density of the access points, etc., right? So we use those adjustment factors to reduce the free flow speed from the base condition to the existing condition. But this again, it will not be as accurate as the direct field measurement, right? So because it's not taking into account the demand or anything, right? So it's therefore this is the least. This would be the least preferred, right? So this will be the most preferred way, and C will be the least preferred way. Right, so if we can do if we have the option of doing all A, B, and C, so we should go with A, so that we can get more precise and accurate measurement of the free flow speed. Okay, so moving on to question number 2, you have to accept or reject the statement. So in LOS analysis of two-lane highways, demand adjustment for ATS is carried out for class 1 class 2 and class 3 highways. Okay, so we will take 1 minute to answer this. You have to go back to the framework that we discussed. Expand whether and decide whether ATS adjustment is done for the three classes of the two-lane highways. Okay, so let's see the answer now. So the right answer is we reject the statement. Why? Because as we saw earlier, so this we are looking at two-lane highways, right? So here we have the three classes: class 1, class 2, and class 3, right? So, and the performance measure, as we already discussed, so it is ATS for class 1 as well as PTSF, right? So the average travel speed and the percentage time spent following. So these two measures are used for class 1. For class 2, so we need the percentage time spent following only. For class 3, we need the percentage of the free flow speed, right? So the question is whether the demand adjustment for ATS carried out for class 1, class 2, and class 3. Right, so because in class 1 we need to estimate the ATS, the demand adjustment will be done, right? So therefore for class 1 it will be done. For class 2, because we need only PTSF, right? So and PTSF and ATS, these are not dependent on each other, right? So these are independently estimated, so therefore ATS calculation is not needed for class 2. For class 3, so even though it is PFFS, right? So we don't need ATS directly for the final LOS determination. To get PFFS, we need to have ATS, right? So therefore, demand adjustment for ATS will also be done in class 3, right? So for class 1 and class 3, so demand adjustment is done for ATS because it is needed for deriving the performance measure. But in class 2, demand adjustment is not done for ATS because only PTSF is the performance criteria for class 2. Right? So therefore, we reject the statement because it says it is needed for all the three classes, but it is only needed for class 1 and class 3 and not class 2. Okay. So therefore, B is the right answer. Okay. Question number 3. Match the analysis type in column X with the corresponding input precision required in column Y. So here we have column X, three types of analysis that we do. One is the operational analysis, second is design analysis, and third is planning and preliminary engineering. So column Y is the level of precision in the input data that we need. So option A is there is use of some default values. Option B is there is extensive use of default values, and option C is no or minimal use of the default values. Right. So we have to match which level of precision is required in which type of analysis that we do, right? So this is with respect to the urban street segments that we saw. Okay. Again, maybe 1 or 2 minutes. Okay, so let's take a look at the answer. So the right answer is option C, where 1 is matched with C, 2 is matched with A, and 3 is matched with B. Okay, okay. So here we are looking at the type of the analysis done for urban street segment and the input precision that is required, right? So we have so the planning. So we have the planning analysis, we have design analysis, and we have operational analysis, right? So as I said earlier, so this is the order in which the complexity increases, right? So planning is the least complex one, right? So and then design, then finally operation. So along with this complexity, so the data need is also increases in this particular order, right? So the data need and the detail that is involved. Okay. So, which means planning, you don't need too much data, so you'll assume mostly default values if you do not have the data, right? So, with minimal data collection, because you don't need such a detailed analysis. So, when you are like looking at which are the feasible type of solutions that we can look at, right? So, this is like a preliminary analysis. So, you don't need too much detail. So, in for the design, you need little more detail of the current conditions are the conditions for which you will be designing it for, right? So the anticipated one. So you need little more data, and then finally operational one requires the current conditions or the field conditions. So therefore, this is the most data intensive and detailed analysis operational, right? So if we look at that, so that is given so the right options given in the columns are for operational, we need the extensive use of the sorry, not extensive, no minimal use, no or minimal use, right? So here we are looking at the use of default value. So if we are using the default value, which means that right, so you're not estimating, you're not collecting the data, right? So that means it's a lesser level of detail. So for operation, we need the more level of detail. So therefore, it has the minimal or no use of default values. And then design is intermediate, right? So that we can use somewhat default values. For planning, we can use extremely or extensive use of the default value, right? So therefore, 1 is matched with C, 2 with A, and 3 with B, which is given in option C. Okay, question number 4 is, which of the following are the performance measures for determining the LOS of urban street segments? So options are density, travel speed, volume to capacity ratio, and percentage time spent following. Right, so this is a multiple answer question, right? So more than one option may be correct, right? So one or more than one may be correct for this question. Okay, so I think I take a look at the answer now. So the right answer for this question is it is both options B travel speed and option C volume to capacity ratio. Okay, so here we are looking at LOS determination of urban street segments, right? So far we are looking at the highways, right? So multi-lane highways and two-lane highways. So now we are moving on to urban street segments. So obviously the performance measure that we use depends on the facility that we are analyzing, right? So because LOS determination, it is both mode specific as well as the facility specific, right? So depending on the type of mode and the type of facility that we are analyzing, the way in which we determine the LOS varies. Okay. So here we are given with four options. So we know density. Where did we look at density? The density was used for freeways and multi-lane highways. Right. So density is the performance measure for freeways and multi-lane highways, and percentage time spent following. So this we just now looked at, right? So this is for two-lane highways, and more specifically, is for class one and class two two-lane highways, right? So for class three, it is percentage of the free flow speed, right? So but this is only used for class one and class two, right? So therefore, we have two things left. One is travel speed and volume to capacity ratio. So these two together are used for urban street segments. Right? So more specifically, this is the travel speed and the V by C ratio for through movement. Right? So we consider this because at an intersection, right? So because our urban street segments, the boundaries are nothing but intersections, right? So that's how we were defining the urban street segments. So at intersections, we could have through movements as well as turning movements, right? So this is the through movement, and then these are the turning movements. We could have left turning, right turning, right? So and these two performance measures, travel speed and volume to capacity ratio, so these are measured only for the through movement and then used in the LOS analysis. So why? Because this travel speed, it gives you a sense of the delay that is incurred when you are passing through the intersection, right? So that's one of the measures, and the second is volume to capacity ratio. So this is giving you a sense of whether there is undersaturation or oversaturation and so on, right? So these two measures together. So this is like a telling you the level of mobility that you can expect from this intersection, right? So for the given demand conditions, right? So the volume to capacity ratio and the travel speed together are used for the LOS determination. Therefore, B and C are the right answers, right? So for urban street segment. Okay, moving on to question number 5 is under which of the following LOS levels is a facility said to be operating in a stable condition? So options are LOS A, LOS B, LOS C, and LOS D. Let's take a look at the answer now. The right answer is option C. It is LOS. Okay. So as we know, LOS, tells us about the quality of the service that we see that we see from a facility, right? So we have six different levels, starting from LOS A to LOS F, LOS B, LOS C, LOS D, LOS E, and LOS F, right? So we have LOS A as the best, and LOS is the worst, quality of service, right? So here we are talking about stable condition. So what is stable condition? So which means that for when as the demand increases, you're going to have increased delay, right? So this being right. So with increasing demand, you are going to experience increasing delays, right? So because the capacity of the facility is fixed, right? So with increasing demand, the quality is going to go lower and lower only, right? Which quality you can define in terms of different measures. It's a delay, speed, and so on, right? So and again, this measure, as we know, depends on the facility that we are analyzing, right? So let's just take one example of anything that represents the quality, right? So let's take speed itself, right? So this is going to it's not going to be going up and down, right? It's going to go in one direction, right? It's going to keep deteriorating. So that we know with respect to demand. So what by stable condition means, right? So if demand is at some particular level, right? So at a given LOS, right? And if we nudge this demand, right? So if we increase the demand, the quality is going to go down, right? But if we can bring the demand back, right? So by the same amount, we have to see similar recovery in the quality as well, right? So this, if by increasing demand by say 50 vehicles per hour, right, the speed is going down by some X%. If we remove the demand by 50 vehicles per hour, we should see that the X percentage decrease to be recovered, right? So if that happens, so then we call this to be a stable condition, right? Uh, so here, if we look at it, so A and B, so these are more, in the free flow or close to free flow conditions. That's where we see these two LOS, right? So which means that we don't, even with increase in demand, slight increase in demand, we won't see too much deterioration, right? So this will be like, in LOSA, we'll have 80% of free flow speed that we can see, something in that range. For LOSB, something like 67 to 80% of the free flow speed. So this is the condition that will exist, right? So here we see that these are already operating in the free flow conditions, right? Or close to free flow conditions. So there's not going to be much, effect on the quality. So when it comes to LOC, so here it will be in the 50 to 67% range of this free flow speed, right? So this is the stable condition, right? So here we will see that. So when when the demand increases and the quality deteriorates, and the demand goes back, right? So the quality will also quickly recover, right? So that therefore this is a stable range of operation, whereas LOSD, this represents unstable operations, right? So which means that even if you increase demand slightly, right? So increase in the demand, so even if it is slight, so the increase in the delays will be significant, right? So you'll have disproportionate increases in the delays or deterioration in the quality. Therefore, this is an unstable condition. And then LOSE is basically this is close to capacity condition, right? So this is again one of the worst conditions that we can have. And LOSF is when breakdown happens, right? Which means the capacity has been exceeded. So this is breakdown condition, which means V is greater than C. We have volumes exceeding the capacity. Therefore, this facility is no longer able to service the demand level that is coming in, right? So therefore, so there will be excessive delays that we can observe in LOS, right? So among these, so therefore C is the C is the level of service. It's where stable condition exists, right? So we are using like optimal use of these conditions without compromising too much on the quality. Okay, question number 6. So this is an accept or reject the statement. So sustained spillback at an urban street segment results from the oversaturation. So you have to either accept or reject the statement. Okay, again, this is with respect to the urban street segments. Okay, so let's look at the answer. The right answer is option A. We accept the statement, right? The given statement is correct. Okay, here we are talking about spillbacks at urban street segments, right? So here, so this generally happens with signalized intersections forming the boundaries of your the urban street segment, right? So as we know, right? So we have, let's say we are analyzing this particular segment. Okay, so we have an upstream signal and we have a downstream signal, right? So when we are talking about spillback, so what does it mean? So from the upstream signal, some demand is coming into this segment, right? So in each cycle we'll have some inflow, some demand that is coming in, and let's say this is V in, right? And then this is V out, right? So in every cycle, some vehicles will pass through the downstream signal as well, right? So what is spillback? So if your V out is lesser than V in, right? So in that case, what will happen? So every vehicle that is coming in is not all the vehicles that have come in one cycle are able to get out of this downstream signal. So which means there will be queue that will be growing in, right? So when the signal is red, so when the signal is red, there will be vehicles queuing up in the urban street segment, right? So that's what we call as the spillback, right? So whatever is coming in, they are not able to go out, so they have spillback into the next cycle. So they have to form a queue and then wait. So what do we mean by sustained spillback? So let us say during the red period, some V prime number of vehicles are queued up, right? And the signal turns green, right? And then say V double prime number of vehicles are going out. Okay, so if V prime uh, you know greater than V double prime, so what does this mean? So the number of vehicles that were in the queue, right, is more than the number of vehicles that got out during the green phase of this downstream signal, which means that the total queue has not cleared, right? So some portion of the queue will be cleared, but some portion of the queue, which is V prime, V double prime, so this will still be remaining and the signal will turn red, so they will be still there in the queue, right? So which means some spillback is sustained for multiple cycle lengths, right? So that's what is the sustained spillback. So if all the accumulated queue is not cleared in that same cycle, right? So which means they'll have to wait for multiple cycles to pass through this intersection. So that's the sustained spillback, right? So if it is the other way around, if V prime is less than V double prime, right? So in that less than or equal to, so in that case, whatever Q was accumulated in one cycle, so that will be cleared in the immediately next cycle, right? So that is called as cyclic spillback, right? So here we are talking about sustained spillback, and the statement says the sustained spillback is because of oversaturation, right? So and this is correct. Why? Because what is oversaturation? Oversaturation means the volume is greater than the capacity, right? So which means this is so again volume cannot be greater, so it will be the demand, right? So the demand is more than the capacity, so that's why you have higher inflows than what can go through the signal, right? So therefore you'll have longer queues than what this downstream intersection can service in one signal length, right? So when that happens, so you'll have sustained spillback, right? So if you have lesser than, so the capacity is in terms of the saturation flow rate of this downstream signal, right? So if we have inflow coming from the upstream signal lesser than the saturation flow rate, so in that case you'll have undersaturated condition. So and that can be that will only result in a cyclic spillback. And so therefore this given statement is correct. Okay, question number 7 is a numerical. So we have to determine the PTSF value for a 6-mile 2-lane highway in rolling terrain. Okay, so some traffic data is given for this highway. So the volume is 1600 vehicles per hour, and this is the two-way volume, right? So this is not for any one direction, but both the directions combined. The percentage of trucks in this traffic stream are 14%, and percentage of recreational vehicles is 4%. The peak hour factor is 0.95, and the directional split is 50-50, which means 50% in one direction, 50% in the opposite direction, and the percentage of no passing zones is 50%. Okay, so using this, we have to calculate the PTSF value, and we have some tables given from the HCM manual, for calculating these adjustment factors that we will need. Okay, so we have adjustment factor for the terrain and the grades, and also for PCU values for trucks and recreational vehicles. And then this we'll need to calculate the base PTSF. For that, the equation requires A and B, so that table, as well as the adjustment factor for the no passing. Okay, so let's see how to solve this problem. So the answer is it is 82%, right? So but we look at the detailed solution of how to do this, right? So for PTSF calculation, right? So we don't need free flow speed, right? So directly we can start with the demand adjustment and then estimate the the PTSF, right? So first step is to do demand adjustment for PTSF. So how do we do? So what do we know initially? So we know that the flow in the design direction. Let's say we'll be analyzing it in one direction, right? So we won't be analyzing both the directions together, right? So we'll be analyzing in one direction. So let's say the non-adjusted demand, let's call it VD prime, right? So what is that? So that we know it is 50% of 1600, which is 800 vehicles per hour, right? So why is this? Because 1600 is the demand in both directions together, and we know the directional split is 50-50, right? So which means 800 in one direction and 800 in the opposite direction, right? So opposite direction original flow is also 800 vehicles per hour, right? So both directions carry equal flow, right? So this needs to be adjusted for the PTSF calculation. So how do we adjust it? So we calculate the adjusted PTSF. So VD for PTSF calculation. So that is this original value divided by the peak hour factor into the adjustment for the grade and the adjustment done for heavy vehicles. Right? So this is the formula, right? So this is how we adjust the the original flow for PTSF calculation. So in this we know what this VD prime is, right? So, and also we know what is the PHF value, right? So that is 0.95 given in the problem. So all that we need to know is the adjustment factors for the grade, which is FG, and the adjustment factor for the heavy vehicle FHV, right? So these two needs to be calculated, right? So first, let's say how to get the FG value, right? So for that, let's go back, see the table, right? So this is the table which gives us the FG value, right? So exhibit 1560 from HCM 2016. So what do we need? So for this, we need to know what is the type of terrain, whether it is a level terrain or a rolling terrain. So that is one input that we need. And the second is what is the directional demand flow rate, right? So here you have to remember that this is not the original demand, but the demand flow rate, right? So which means we have to consider the peak hour factor and then adjust it to get the demand flow rate, and then based on that and the terrain, we will get the adjustment factor. So what is the demand flow rate in our case? So we know we saw that demand is 800, right? So vehicles per hour. What is the demand flow rate? So let's just call that VD, right? Not VD prime. So that will be VD prime divided by the PHF, right? So this will give you the demand flow rate. So that is 800 by 0.95, which is 842 vehicles per hour, right? So this 842 is our input, and the other input is the type of terrain, and it is given that this two-lane highway is in a rolling terrain, right? So which means we have to look at this particular column, and the row which we will be looking at is corresponding to 842. But as we see from this table, we don't have the value for 842. There is a value for 800. There is a value for more than or equal to 900. So what do we do in this case? So whenever we don't have the exact value that we are looking for, we just have to assume this the variation within these two values is linear, and then we will interpolate for the value that we want. Okay, so how do we do this? So for 800 and rolling terrain, right? So the value is 0.99, the FG value, and for 900 it is 1.00, right? So we need to know what is it for 800. So 1 minus 0.99 by 900 minus 800. So this is same as, so the FG that we want minus 0.99 divided by 842 minus 800, right? So we are linearly interpolating between 800 and 900 to get it. So if you calculate this, so the value will be, FG will be coming at approximately 0.9, right? So it will be a little more than 0.99, but there will be only third decimal changes, so we can approximately consider it to be 0.99 itself. Okay, so therefore FG is 0.99 for our case. Okay, so next we want the FHV. So how do we get FHV? So FHV is nothing but 1 over 1 plus the percentage of trucks into the equivalency factor for trucks minus 1 plus the percentage of recreational vehicles into the equivalency factor for the recreational vehicles minus 1, right? So this is the formula. So in this, we know what is the percentage of trucks and the percentage of recreational vehicles, right? So it is 14% for trucks and 4% for the recreational vehicles. So all we need to know is the equivalency factor, right? So we are because these are different classes of vehicles, so we have this equivalency factors to convert them into into the PCUs, right? So that's what this ET and ER are. So how do we get that? So that's where we use this particular table, which is exhibit 1580, right? So here for different vehicle types, which is trucks and recreational vehicles, we know the equivalency factors for a given terrain and the demand flow rate. Okay, so already we know the demand flow rate, which is 842, and also it is rolling terrain. Okay, so first for ET, see, so the values are here constant for the rolling terrain, right? is 111. Therefore, for 842 also, if you interpolate, it's going to be 1 because it is constant. Okay, so ET is 1. So RV, so it doesn't depend on the flow. For all flows, it is 1 in the rolling terrain, right? So therefore, both ET as well as ER are 1. So ET is equal to 1, ER also is equal to 1, right? So therefore, can go for the calculation. So FH will be 1 by 1 plus, so 14% of 1 minus 1 plus 4% of ER is also 1. See, because 1 minus 1 is 0, so these two terms are not going to be having any impact. So it's going to be 1. FHV is 1. Okay, so we can finally calculate the adjusted demand for PTSR because we know all the terms here now. So what is VD prime? So VD prime is 800. So the original flow in the design direction divided by PHF is 0.95. And what is FG for PTSF? It is 0.99 from here. Okay, and FHV is 1, right? So from here we calculate the adjusted demand. So how much this will be? So this again comes out to be 842, right? Because this is almost close to 1. So this is same as our adjusted our other demand flow rate. So this is 842, in terms of passenger cars, right? So it is in passenger car equivalent units. So PC per hour. Okay, so this is the first step that we have to do. So once we have the BD, so then we can go for estimating the base PTSF value. Okay, so this is the second step. So what is the base PTSF? So base PTSF for the design direction. So that is nothing but 100 into 1 minus e to the power a into VD for PTSF raised to the power b. Okay, so we use this adjusted demand flow, adjusted demand for PTSF, right? So that is VD PTSF, right? And then use this equation, right? So that gives us the base PTSF value. Okay, so in this equation, so we know VD PTSF, but we don't know the constants A and B, right? So how do we get it? So that is given in the third table here, exhibit 1520. Okay, so here this coefficient A and B, these are dependent on not the direction in which we are analyzing, but the opposing flow rate. Okay, VO, right? So what is opposing flow rate in our case? So opposing flow rate is also 800 by 0.95, which is 842 vehicles per hour. Why? Because we have a 50-50 split, right? So the direction in which we are analyzing and the opposite direction, they are carrying equal flows and their flow rate is also the same, right? So therefore 842 is the flow rate in the opposite direction as well. So using that, we have to get the values of A and B. So again, as we see that 842 is not there in the table, right? So we have to interpolate between 800 and 1000. Okay, so for A, so it will be minus 0.0049 plus 0.0045 divided by 1000 minus 800. So this is equal to A plus 0.0045 divided by 842 minus 800. Right? So if you solve this, you will get A is equal to minus 0.0046. Okay, so we have interpolated and got the value of A. Similar steps you can follow, and then you will get the value of B as 0.832. Right, so we got the value for A and B. We can substitute that in our PTSL equation. So this will be 100 into 1 minus e to the power minus 0.0046 into the adjusted demand is 842 raised to the power of 0.832, right? So this gives you the base value as 71.3. 10% because it's the percentage time spent following, right? So this is the base condition. So then we have to adjust this base condition for the existing condition, right? So that will give you the PTSF. So what is the adjustment that we will do? So the adjustment is, so one adjustment is for, there are two adjustment factors. So one is for PTSF, you have only a single adjustment factor, so which is for the no passing zone. Okay, so it is F and P into the design PTSF demand plus the design in the opposing sides PTSF demand. Okay, so this we have calculated 842. Similar exercise you have to do for the other direction, but since here these are 50, these are carrying equal flows on both directions, so the opposite direction will also have the same PTSF adjusted demand, right? So therefore, all we need now is the no passing zone adjustment. So how do we get that? So that's where we use this last table. So here we need the two-way flow rate, right, and the adjustment factor for the no passing zone, so which is 50% in our case, right? And what is the two-way flow rate? So which is 1600, right? So again you have to interpolate between 1400 and 2000, right? So if you do this interpolation between those two, you will get this F and P as 21. Okay, so it is 25 for 1400, 16.6 for 2000. So our value is in between those two and it will be 21. Okay, so it is 71.3 minus 21 into, so 842 divided by 842 plus 842. Okay, so this is nothing, this will be 81.88%. Okay, so approximately 82% is the percentage of the time that is spent following. Okay, so those are the three steps that we need. The first one is to adjust the demand, right? So the given demand for PTSF, so which depends on your gradient, the proportion of the heavy vehicles and also the peak hour factor, right? So you will get the adjusted demand in passenger cars per hour. Then you have to calculate the base PTSF, which depends on your adjusted demand. Okay, and also the two coefficients. So you need to estimate it based on the opposing flow, right? And then the third condition is to adjust this base PTSF based on the no passing zone and the adjusted demand. Okay, so you will get the PTSF. So with this, if it is a class 2 highway, we can directly go for the LOS determination, right? But if it is class 1, this is one of the performance measure. The other, like ATS, we have to follow similar steps to calculate it. Okay, so but here the question was only to find the PTSF, so we will stop here for this question. Okay, question number 8 is, we have to continue with the same facility that we were analyzing. So use the data provided in the previous question to estimate the average travel speed, ATS, right? So here we need little more information for ATS calculation, so which is the base free flow speed. We can take that as the posted speed of 60 miles per hour, and the section length is 6 miles, so we already moved from the previous question. Lane width is 11 feet, shoulder width is 4 feet, and the access point density is 20 points per mile. Okay, so these are the things, and then we have the adjustment factors corresponding for the ATS calculations given here. Okay, so let's do that to get the ATS. So the final value is 38.6. Okay, you can verify this if we are doing it independently. So for ATS, we need to know the free flow speed. Okay, so before we do the demand adjustment, we'll start with estimating the free flow speed. Okay, so we can take, it is given that the base free flow speed is the same as the posted speed of 60 miles per hour, right? So first, how do we get the free flow speed? So free flow speed will be the base free flow speed minus the adjustment factor for the shoulder width and also the access point density. Okay, we have the two adjustment factors for free flow speed. So this will be 60 minus. So what is FLS? So FLS, it's based on the lane width as well as the shoulder width. Okay. So in our case, we have 11 feet as the lane width and 4 feet as the shoulder, right? So 11 feet means it is this particular part greater than equal to 11 and less than 12, and then for shoulder width is 4 feet, which falls here, greater than equal to 4 and less than 6, right? So the intersection of those two gives us an adjustment factor of 1.7, right? So this is our FLS. And then what is FA? That is the access points per mile. So that is 20 given in the question, right? So for 20, we directly have a value, and that is reduction of 5 miles per hour. Okay, so we got both FA as well as FLS, right? So we can calculate the free flow speed. So it is minus 1.7 minus 5. Okay, so that gives you 53.3 miles per hour as your free flow speed estimate. Okay, so this is one part. Next, we have to go for the demand adjustment, similar to what we did for PTSF. Okay, next is demand adjustment for ATS. Right, so the adjusted demand is in the same way. So this will be VD by BHF into FG, but this FG is not the same as what we used earlier. So this is corresponding to ATS, okay, and FHV again, this is for ATS, right? So we can't use the same value that we used for PTSF, right? So those adjustment factors are different from the adjustment factors here for ATS, right? So again, we know what is VD. So VD is 800. So this is not different because it's the same facility that we are still analyzing. So PHF is also the same. So we need FG. So what is FG here? So here, so FG again, it depends on your direction flow rate as well as the terrain. Okay, here again we are looking at rolling terrain, and the demand flow rate is 842, right? So it is 800 by 0.95. So that is VD by PHF. Right, so 842. So this table is not different, right? So we have the same thing. So between 800 and 900, varying from 0.99 to 1. So we already calculated this. So this is not different. So this will again be 0.99 for 842. Okay. So this is 0.99 because the table didn't change. But for FHV, so what was FHV? It is 1 by 1 plus PT into PT minus 1 plus PR into ER minus 1, right? So we need to find the ET and ER values. So ET value, so this is different from the PTSF values. So here the directional demand rate, so between these two, so for rolling terrain, so it will be between 1.4 and 1.3. Okay, so again we need to interpolate it. So for 800, so is 1.3 minus 1.4 by 900 minus 800. So it should be ET minus 1.4 by 842 minus 800. So this again, so there won't be much change, right? So it will be only in the third decimal changes. So therefore ET we can take it as 1.4 because it's more closer to 800. So similarly, for ER, it doesn't depend on your flow rate. So for all flows, it is 1.1, right? So ER is 1.1. Okay. So which means FHV will be 1 by 1 plus 14% into 1.4 minus 1 plus 4% is the percentage of RVs into 1.1 minus 1, right? So you simplify this. So what do you get? So FHV would be coming around 0.943. Okay, so we got FG, we got FHV, so we can substitute that and it will be 0.99 and 0.943. So this will give you the adjusted demand for the ATS calculation. So that comes out as 902 TC per hour, right? So see this, even though the inflow is the same, right? So but for PTSF we got a different adjusted demand, but for ATS we are getting a different adjusted demand, right? So that you have to keep in mind. You can't use the same value for both, right? So finally, so we can go for ATS calculation. So that is the third step. So ATS for your design direction, so that is free flow speed. So that's why we calculate the free flow speed, because it is needed for this step. So free flow speed minus the equation is 0.00776 into the adjusted demand for ATS in the design direction plus the adjusted demand in the opposite direction minus the adjustment factor for the no passing zone. So again, this is for ATS, right? So this is different from the previous one. So in this we know the free flow speed, we know the VD in the ATS for ATS, the adjusted demand. Again, because this is a 50-50 split, so VO will also be the same. Otherwise, we have to redo this the previous step for the opposite direction, and then the FNP is what is needed now. Okay, so let's calculate what the FNP value is. So what does it depend on? It depends on right. So again here opposing flow values, flow rate, as well as the percentage zones, and also depending on your free flow speed, right? So here we are looking at so based on the previous question data, it is 50% is the no passing zone, and the opposing flow rate is 842, right? So based on that, so again the free flow speed is 53.3, so which means that so two interpolations need to be done. One is for the opposing flow, right? So it is between 800 and 1000. So for 842 at 50%, so between 0.9 and 0.7, you have to interpolate and get one value. So that is for the free flow speed of 55. Next, you have to repeat that for a free flow speed of 50, right? So which means you have to interpolate between these two values. So you'll get your second estimate, and then you have to interpolate between these two for a free flow speed of 53.3, right? So three interpolations need to be done, right? So if you do that, you will find that it will come out to be FNPS 0.7. Okay, so that is our no passing zone adjustment factor. So free flow speed is 53.3 minus 0.00776 into adjusted demand is 902 in the design direction and the opposite direction as well, minus FNPS 0.7. Okay, so this will come out to be 53.3 minus 1.4 minus 0.7, so which is 38.6 miles per hour. Okay, so this gives you the ATS value in the design direction. Okay, so this is the second performance measure that we need if this is a class 1 highway, right? So if it is a class 2, only the PTSF that we calculated earlier is enough. But if it is a class 1, so we need the previous PTSF value as well as this ATS value, right? So to determine the LOS. Okay, so this completes question 8. So where we needed only in ATS. Okay, so moving on to question number 9. Okay, so here we need to again make use of the data from question 7 and 8 and also the results that we got to determine the level of service for that segment, assuming that in option in part A it to be a class 1 highway, and in part B assuming it as a class 2 highway, right? So here we have to put those two results together to determine the LOS. Okay, so here is the table that gives us the LOS, the performance measure ranges for different LOS conditions depending on the type of highway. Okay, so what did we find? We found that the PTSF was 82% and the ATS is 38, right? So let's check. Yeah, 38.6. Right, so we calculated both the performance measures. So first for part A, we'll assume that it's a class 1 highway. Okay, if it is a class 1 highway, so we need to use both ATS and PTSF to determine the LOS. Okay, first as looking at ATS value, which is 38.6. So 38.6 is lesser than or equal to 40, right? So according to ATS, LOS is E. Okay, then looking at PTSF, which is 82%. So 82% is more than 80, right? So according to PTSF, also this is LOS, right? So these both agree. So the overall LOS is E for class 1. Okay, if it is a class 1 highway, it is operating at level of service E. Okay, if we assume this is to be a class 2 highway, then we don't need ATS, we need to only look at PTSF value. Okay, so what is the PTSF? It is 82%, right? So 82% is greater than 70 and less than 85, so which is falling under LOS D. So according to PTSF, for class 2 it is LOS D. There is only one measure. So if it is a class 2 highway, it is operating at LOS level D. But if it is a class 1 highway, it is operating at LOS level E. Right? So it's the same facility. The results are same, the measures are same, but depending on the type of the facility, the LOS varies. Right? So that's what we were looking at earlier. So it is facility dependent, and also it will change for the different modes. If you analyze for a different mode of travel, so that will also vary. Okay, so those are the right answer for option A, which is for part A, which is for class 1, LOZ. For part B, which is class 2, it is LOS. Okay, so that's how we analyze the two-lane highways as per the HCM. Okay, so with that, we are coming to the end of the questions for week 5. Okay, if you have any doubts or queries, you can post them in the discussion forum, right? So, and then we can get it answered. Okay, so with that, we'll close this session and meet again next Saturday, at 4 p.m. Okay, thank you for